Hello. In this video, we will be looking at how to find the area between two curves. So the type of problem that presents itself to us is if you were given two functions, f of x and g of x, how would you figure out how much area is in between them? Well, visually what it would look like, the way we're going to approach this, is first of all you would find out how much area is underneath the top curve. Then you could figure out how much area is underneath the bottom curve. And if you imagine overlaying this first graph right on top of this second graph, you would find that this bottom curve overlaps some of the area from the first curve. So if you subtract that second area from this first area, all we would be left with is the area between the two curves. So that is our intuition about how we are going to proceed. Let's look at the way we would notate this. So to find area between two curves, a definite integral tells you the area underneath a curve from one point to another point. If we constructed one definite integral for our first function and then another definite integral for our second function, what would happen is we would have the first area and then we could subtract off the smaller area like we would intend. One of the properties of definite integrals is that if you are ever subtracting two definite integrals that have the same limits of integration, you can combine them into one definite integral. So we see this written down here. Instead of computing one area and then a separate area and then subtracting them, we can just subtract the two functions, and after we've subtracted the two functions, compute the definite integral using those same limits of integration. All right, so with that in mind, let's jump into our first example. All right, well, let's look at our first example. I've gone ahead and graphed this in Desmos. Let me write down what the functions are. I'm considering f of x to be equal to 25, and I'm considering g of x to be equal to x squared minus 4x plus 4. And I'm only going to consider the area that's shaded. So we start with an x value of 0. That point that I'm indicating there should be 0, 25. And then we're going up until an x value of 7, so that would be the point 7, 25. All right, well, according to the formula, if I wanted to compute the area, which is what I would like to do, that's going to be equal to the definite integral. I'm going to have to list limits of integration, and then it's going to be the f of x function minus the g of x function. This, of course, is going to happen with respect to x. Now, when you think about f of x and g of x, what's important about these is that the first function you list is the function that is on top in the graph, and the second function you list is the function that's underneath in the graph. So I have set this up. I've called this first one f, I called the second one g, so that it fits nicely into this f minus g format. But regardless of what I had called that, the 25 is going to have to go first because it's on top. Okay, the next thing we want to think about is the limits of integration. So where does the shading begin? It begins at the x value of 0. We see that down here. And then where does the shading stop? Well, if we trace all the way up here, it stops at the x value of 7. So my limits of integration are going to be 0 to 7. And as a reminder, if you're integrating with respect to x, your limits of integration are always going to have to be x values. Okay, so let's go ahead and substitute the two functions in. The area is going to be definite integral 0 to 7. I start with 25, then I'm subtracting the second function, x squared minus 4x plus 4. This is all happening with respect to x. I do want to simplify that. So area is equal to definite integral 0 to 7. That's going to be negative x squared plus 4x. Then 25 minus 4 should be plus 21. At this point, you can apply the fundamental theorem of calculus, which says that you find an antiderivative, negative x cubed over 3 plus 4x squared over 2 plus 21x, then evaluate it at the two limits of integration. All right, we want to plug 7 into this function. I'll write that number down here. Then I'll put 0 into this function, and we'll subtract the two results. And what I get is, is 130.6667 minus 0. Now that's what the calculator is telling me. So we do want to compute or write an exact number. So let's go ahead and convert this to an improper fraction. Doing that in my calculator really quick, I get 392 thirds. So 392 over 3. This is the exact area that was trapped between the f function and the g function over the indicated interval. So the interval was 0 to 7. All right, let's look at another example. All right, here is the second example. We want to consider these three lines. Y is equal to the cubed root of x. The second line is x equals 6, and then the third line is y is equal to 3 minus 2x. All right, I would like us to find the area trapped between these two curves. So at its core, area between two curves is a definite integral. We're going to have to come up with limits of integration. You have a top function and you have a bottom function. And of course, we are integrating with respect to x. So there's a couple of things that we would need to determine. First of all, what is the top function? Secondly, what is the bottom function? Hopefully that's fairly easy. When we look at this y equals cubed root of x up here definitely seems to be the top function, so I'll insert that here. Then y is equal to 3 minus 2x is the function that's underneath that, so that'll be the bottom function. This equation here, x equals 6, really is not underneath or above either of the two functions. This just indicates where we are stopping with our integration. So x equals 6 is going to be our upper limit of integration because we're going to integrate from whatever this x value is all the way up until this value. Okay, so let's go ahead and put in the numbers that we're confident with. Definite integral, we are integrating from some x value that's unknown, this leftmost x value, all the way up until this rightmost x value. Okay, we know that the rightmost x value is 6. Top function is the cubed root of x, and since I know that I'm about to find an antiderivative of this function, I'm going to go ahead and list this as x to the 1/3. Then we subtract the bottom function, 3 minus 2x, and the only missing piece of information, the only thing we need to be able to finalize this computation is going to be this lower limit of integration. So we look at these two functions and we ask ourselves, when would this function on the left be equal to, or I guess underneath, be equal to this function on top? Now, there's a number of ways that you could try to approach this. It could be clear based on the graph where, like, what this intersection point is. If it's not, what you would have to do is you would have to set the two things equal to each other. So when is the cubed root of x equal to 3 minus 2x? And then you would have to use algebra to solve that. I'm not really interested in getting into the algebra too much, so I will just tell you right now that these two things intersect at the point 1, 1. So the x value where they intersect is 1. Now that I've told you, and maybe you assumed this initially, you could just verify if you plug in 1 on the left, it should be the same as if you plug in 1 on the right. We get the same y value both times. Okay, we have a lower limit of integration then. That's the leftmost x value where the shading started. Now that we have our definite integral set up, we can go ahead and we can compute what this is equal to. So we find the antiderivative of this function. I guess even before I do that, it's probably going to be helpful to distribute the negative into parentheses. So one last time, let's write the definite integral down, that's x to the 1/3 minus 3 plus 2x. Okay, now I feel ready to find the antiderivative. This would be x raised up to the, I'm going to need to increase the value of this by 1, so that should be 4/3. Then you immediately divide by 4/3. If you divide by 4/3, that would be the same thing as multiplying by 3/4. So I'm putting this in red just to indicate that, like, I had to think about that. Dividing by 4/3 ended up resulting in multiplying by 3/4. Okay, then we are subtracting 3x. We're adding 2x squared over 2. So I increase the size of the exponent by 1. I'm going to immediately divide by whatever the new exponent is. So then I'm just reducing 2 divided by 2 to be 1. If you like to see this, you could write 2 over 2. It's not going to hurt, but it's also fine to not show that and to just immediately reduce it as you write it. All right, once you've found an antiderivative, we are evaluating this at the two endpoints. So that's, those limits of integration are 6 and 1. All right, I'll pause the video. Let's take a minute to plug 6 into this function. We'll write that answer down here. Then I'll put 1 into the function. We'll write that answer down here, and then we'll subtract the two results at the end. All right, when I plug these numbers in, I get 26.177 for the first value when the function's evaluated at 6. When the function is evaluated at 1, I got negative 1.25. If I go ahead and subtract 26.177 minus a negative 1.25, I get 27.427. All right, and that is the final answer here. So let me go ahead and box that in. This is the exact area trapped in between this top curve and this bottom curve from the x value of 1 all the way up until the x value of 6. All right, the last example I would like to look at is computing the area between two curves, but in this case, we don't have one of the curves consistently above the other one. They're going to trade places as x values increase. So let's go ahead and write down what the equation of the first curve is. We have y is equal to x cubed minus 2x. So if you want to trace it out, that's the one that starts down here, comes up, hits 0, 0, then goes back down, and then continues on like this. Okay, so that is this curve. The second curve that we have is going to be y is equal to x squared. Y equals x squared, and that is this curve. It's the one that starts up here on the top left. You kind of go down through 0, 0. And then for the second part of the shaded region, it ends up being above the x cubed graph. All right, so when we have a situation like this where one curve is on top for one area and another curve is on top for a second area, you're going to have to split this into two definite integrals. So the area, now in my example, I colored them differently. So we have a purple area and a green area. First of all, you would have to think about the purple area, and then we would add on a definite integral that represents the green area. Okay, so let's start with the purple area. Here we notice that x cubed minus 2x is on top, and the bottom function would be x squared, so we'll subtract x squared. When you look at that, the limits of integration, definitely the upper limit of integration is 0. It's pretty clear that 0 is the rightmost x value for the purple region. When you look here, like, what is this leftmost x value? It's just whatever x value is over here, where this thing would equal this thing. If you want to take the time to set them equal to each other and solve that, you should see that one of their intersection points ends up being -1. So let me go ahead and write that down. -1 is that x value. So -1 is my lower limit of integration for the purple area. Well, when we get to the green area, the lower limit of integration is now 0 because that's where the shading starts. And this time it goes all the way up till this second point of intersection. So if you do take the time to set these two things equal to each other and solving them, you should see that they intersect at an x value of 2 as well. Okay, for the green area, we have the x squared function on top, and we have the x cubed minus 2x function underneath. So let's write that's with respect to x. Okay, so we're going to be computing just two separate areas and then adding them together at the end. Let's go ahead and do this. I will take a brief moment to just simplify these. I want to rewrite it without parentheses. This is x cubed minus x squared minus 2x. And then this is 0 to 2, x squared minus x cubed plus 2x. Okay, so my first definite integral, when I take the antiderivative, I get x to the fourth over 4 minus x cubed over 3 minus x squared. I'm going to evaluate that at 0 and -1. Then I'm going to add on the second definite integral. So actually, instead of using all of these equal signs, let me just write down like purple and green. So we have a purple area and a green area. The green area, let's see, the antiderivative there would be x cubed over 3 minus x to the fourth over 4 plus x squared. We're evaluating that one at 2 and at 0. So let me pause the video. We're going to evaluate both of these definite integrals. Just put 0 in here, then put -1 in here, and subtract the two numbers. We'll put 2 into this function, then we'll put 0 into this function, and we will subtract those two results as well. All right, so what I'm getting in my calculator, when I plug both of these numbers in, I got 0 minus -5/12. That ends up just being 5/12. Keep in mind this needs to be a positive number. If that was a negative number, then we would know that we had somehow messed up a part of this process over here. When we evaluate the second integral at these two values, plugging 2 in, we get 8/3. Plugging 0 in, we get 0. 8/3 minus 0 was 8/3. Okay, now we do get to add these two values together, so our total area ends up being 37 over 12, which is approximately 3.1. So if you're looking for an exact answer, you have it here. If an approximation is okay with you, then that's what it is. All right, hopefully this video is helpful as you are thinking about how to compute the area between two curves.